Hello, everyone. I am Ahmed Mahmoud, Head of Data Engineering at DataMindAI, and welcome to the Large Language Model Series, or LLM series, as it were. So, if you work in data, AI, analytics, or decision science, the last 2 years have changed everything in your field. So the large language models, LLM, are not a trend. They are a fundamental shift in what software can do and what your role will look like in 3 years as well. So this series is built for practitioners, not theory for its own sake, but the understanding you need to make real decisions, which model to use and when to build versus buy, how to estimate costs, and how to deploy these systems safely and effectively. We go from the absolute foundations, how machine learns, how language become numbers, all the way through to a technical deep dive on a training course, top 10 models in production today, and the architectures reshaping the entire field. And because this is hands-on series, we also have a practical session where we apply these concepts directly into real workflow, real prompts, and real use cases. Now, this is not, we are not going to do bluffing. There's no bluff here, no jargon for its own sake, just the stuff that matters. Now, if you are interested and if you want to go ahead, I'm glad you are here. Let us get into it. Welcome to the beginners level section. No prior AI knowledge is assumed. If you have been slightly lost in the earlier material, this is where you rebuild cleanly from the ground up. If you are already a technical person, this section has a specific value for you. These are the analogies and examples that work for non-technical stakeholders. Every example here has been tested in boardrooms, in client presentations, in university lectures. They are battle hardened. We covered three things: what an LLM fundamental is, how it works at a mechanical level, and what it can actually do. Grounded in prompts you could type right now and set immediately. The goal of this session is not just comprehension, it is fluency. I want you to leave able to explain this concept to your CTO, your client, your grandmother, anyone who wants to understand LLM using different levels of technical vocabulary, but the same underlying mental model. Let me give you the simplest correct explanation that exists. A large language model is an AI system trained to predict the most likely next word over and over again. Let me repeat. Trained is an AI system, but it is trained to predict the most likely next word over and over again. Yeah, that's it. Everything else is elaboration on that sentence. Now, I know that sounds almost disappointingly simple. Let me convince you it is not. Let us look at the autocomplete. Yeah, but trained on everything ever written. So you can think of the LLM as an autocomplete, but which has been trained on everything ever written. You know the autocomplete on your phone. When you type, for example, happy, it suggests birthday or New Year. That is a tiny language model trained on your personal typing history. A few thousand messages making a next word prediction. Yeah. So your phone have learned like a few thousand messages and it is predicting what it will be the next word. Yeah. So that is autocomplete, we call it. Now, imagine that same autocomplete has read For example, every book instead of thousands messages, every book on projects like 60,000, for example, plus books, the entirety of Wikipedia in 50 languages, most of the public internet as of 2024, a significant fraction of all public GitHub repository, millions of academic papers and legal documents, more text than a human could read in 10,000 lifetimes. It is not just predicting one word, it is predicting the next word, then the next, then the next, building a coherent response token by token. That is what a large language model does. Now, the probability demonstration is also another one. Look at the example on the slide. Given the capital of France is dash, the model assigns probability 99.8% to Paris. Every other word in the vocabulary shares the remaining 0.2%. The model is not looking up Paris in a database. It has learned from reading millions of sentences about France that Paris is the overwhelmingly most likely next word in this context. Now, look at she opened the door and dash, a creative context where no single continuation dominates. Now, so gets 41%, found gets 28%, stepped gets 18%, heard gets 9%. The model picks one from this distribution. Your prompt changed the context. The context determines the probability distribution. So the distribution determines the output. This is why LLM are non-deterministic. When temperature is above zero, the same prompt can produce different responses because the model is sampling from a probability distribution, not retrieving a single fixed answer from a database. Now, the emergency surprise, what nobody predicted. Here's what surprised everyone, including the researchers who built these systems. These models were trained on a single task, predict the next word accurately. Nobody programmed them to translate languages. Nobody programmed them to summarize documents, debug codes, explain scientific concepts, write legal briefs, or compose poetry. Those capabilities were never in the training objective. Yet at a sufficient scale, roughly 10,000 billion parameters, all of those abilities appeared spontaneously without being explicitly taught. Researchers call this emergency, like capability that arise at certain parameters scales that were not present at smaller scale and were not predicted in advance. It is one of the most studied and least understood phenomenon in modern science. Now, if you have a non-technical stakeholder, you can give him this best framing. When explaining LLM to executives or clients who want to a single analogy, imagine hiring someone who has read every book, article, website, legal case, scientific paper, and source code ever published in English, and can recall any of it on demand. But this person has no lived experience outside of text, no physical senses, no memory between separate conversations, and occasionally misremembers things with complete confidence. That hybrid of extraordinary breadth and specific blind spot is what you are working with. Now, we now understand what an LLM is, conceptual at least, but what makes them large? What does the word large actually means in these quantitative terms? The word large refers to the number of parameters, the learned numerical weights inside the model. Let me make this concrete. The stereo equalizer analogy. Imagine an enormous mixing board in a professional recording studio. Not a small home studio board. I mean the large format consoles at Abbey Road or Air Studio with hundreds of faders or knobs, yeah? So each knob controls one small aspect of the sound. So the bass level, the vocal reverb, the kick drum. So you have a knob which controls the bass level and the one which controls the vocal reverb and the second one kick drum, yeah? So this, imagine these knobs, yeah? Now scale that up by a factor of 7 billion. A 7 billion parameter model has 7 billion such knobs. During training, an algorithm called gradient descent turns each knob by an infinite, by very small amount, millions of times until the model prediction matches the training data as well as possible. After training is complete, the knobs are locked permanently. That frozen configuration of 7 billion numbers in the model. It encodes everything the model knows. Yeah. Now, the scale timeline, how fast this has grown. I'm talking about now the parameters, the 7 billion numbers I have given it before. Let us see how much it's been grown in time. So 2018, the birth base, yeah, came up with this 100 million parameters, impressed everyone, won major NLP benchmark. Now, 2019, GPT-2 came with this 1.5 billion parameters. So OpenAI initially withheld the full model, citing safety concerns. Now, 2020, GPT-3 came with 175 billion parameters, or call them knobs, yeah? A qualitative leap. So the first model where prompting becomes a discipline. Imagine, can you see here, 175 billion. It passes the mark of 100 billion, the one we were talking about before. Now, 2022, PALM, which is came with 540 billion parameters. Now, the Google's model trained on 780 billion tokens. Now, 2023 plus GPT-4, Gemini, Ultra, Cloud 3, estimated 1 to 2 trillion parameters, and cost us hundreds of millions to train. So that is a 10,000 increase in parameters count in 5 years. Now, the physical reality, which is the storage, is like 175 billion parameters. Each stores as a 32-bit floating point number, yeah, the 175, and each of them stores a 32-bit floating point number, occupies like 700 gigabytes of storage. That is more than 150 DVD movies, yeah, movies. So the 700 gigabytes of storage is equivalent to 150 DVD movies. You cannot fit GPT-3 weights on a standard laptop hard drive. Running it for inference requires multiple specialized GPU with 80 GB of high bandwidth memory each, connected by enterprise network. This is why you access these models through APIs. The infrastructure required to run them exceeds the resource of most organizations. However, this is changing rapidly. Techniques called quantization reduces each parameter storage from 4 bytes to 1 byte or even half a byte with modest quality loss. So a 7 billion parameter model at 4 bit quantization fits in about 4 gigabytes, smaller than a phone application. This is why Lima 3, 8 billion can now run on a modern laptop. The democratization of AI capability is a real trend. Now, the size, this quality, more parameters does not automatically mean a better model. A 7 billion model trained on 15 trillion tokens of high quality curated data can outperform a 175 billion model trained on 300 billion tokens of noisy web scrape data. The quality, diversity, and curation of training data matters as much as parameters count. So MetaLima 3 at 70 billion trained on 15 trillion tokens perform comparably to or better than GPT-3 at 175 billion trained on 300 billion tokens. More parameters and more data and better data curation together produce better models. So let me repeat this one. So more parameters and more data and better data curation together. Yeah, more parameter, more data, and better data as well. Together produce better models. Now we know now what the model is and what large means in concrete terms. Let us look inside the model itself. What is the architecture that actually enables these capabilities? Now, I'm going to spend a little bit of time on the transformer or the transformer architecture that is. So before 2017, language models existed, yeah, but they were fundamentally limited. The dominant architecture was the recurrent neural network or RNN. So if you were doing data science at that time, so the RNN was the dominant one, and it's more complex one as well. So the metaphor here is someone reading a book one word at a time, keeping a notepad, writing a brief summary as they go, updating it with each new word. Now, the RNN problem was why it failed is because speed. You could not parallelize. Words 5 could not be processed until word 4 was finished. Training on billions of words took months. Now, inference was slow. And the problem number 2 is memory. So the notepad had limited space, a fixed size vector. By the time an RNN had read a 500-word paragraph, it had forgotten the opening sentence. So long-range connections between words far apart in a document were invisible. So concrete failure. So the trophy doesn't fit in the suitcase because it is too large. And RNN often could not confidently resolve that it refers to a trophy. The connection spans too many intervening words for the fixed memory notebook to maintain. So the 2017 breakthrough is that the attention is all you need. In June 2017, 8 researchers at Google published a paper titled Attention is All You Need. It introduces the transformer architecture and launched the modern AI era. The paper has since been cited over 120,000 times. So the central idea, instead of reading text sequentially, process all tokens simultaneously. And instead of a fixed memory, let every token directly attend to every other token, computing a relevance score for each pair. So the trophy can directly consider every word in the sentence simultaneously. No sequential bottleneck, no memory constraint. So the practical results were immediate. Training that took weeks now took days. Models that struggled with long documents now succeeded. The architecture scaled predictably, bigger transformer or reliably better. Now, every major LLM uses this architecture now. So GPT-4, Claudia, Gemini, Lima, DeepSeek, Queen, Mistral, every leading LLM in the production today is a transformer. The original paper proposed it for machine translation. The field has since validated it as a best architecture for essentially every language task and for many non-language tasks as well: protein folding, image generation, audio synthesis as well. So the reason for this architecture dominance is parallelism plus long-range attention plus predictable scaling. These three properties together make a transformer uniquely suited to the modern AI training paradigm of large clusters and massive datasets. Now, what exactly is attention? Let us walk through the mechanism with a specific example because this is the heart of why transformer works so well. The attention mechanism. So self-attention answers one question for every single token. Given the current context, which other tokens in this sequence are most relevant to understanding my meaning, and how much should I weigh each one? So the pronoun resolution example, consider the animal didn't cross the street because it was too tired. When the model processes the word it needs to know what it refers to, animal or street. So self-attention computes a relevance score between it and every other token in the sentence. So the score comes out roughly like this. Animal is 0.92, very high, most relevant. Tired, 0.61, relevant. Predicates apply to the entity. Streets, 0.04, low. Street do not get tired. So they, for example, 0.01, very low. Articles carry little information here. So these scores are used to compute a weighted sum of all tokens representation. The result is a new contextualized representation of it, one that has been enriched by strong contributions from animal and tired and minimal contribution from street. The pronoun is now resolved in the representation itself. The model did not look up a grammar rule about pronoun resolution. It learned from the billions of examples that are statistically co-occurrence pattern between pronouns and animate nouns with a fatigue predicates is very strong. So the resolution falls out of the statistics. So the mechanism in detail is like a query key value. For each token, the model computes three vectors. Yeah, for each token, we'll have three vectors. One is query. What am I looking for? Yeah, and the second is key. What information do I contain? And the third is value. If selected, what do I contribute? Now, the attention score between two tokens is the dot product of the first token's query and the second token's key, a measure of semantic relevance. These scores are normalized, so they sum to one softmax, then used to take a weighted sum of all values vector. The result is a contextualized representation enriched by everything in the token attended to. So let me just repeat this one. So you have the attention score is between two tokens is the dot product of the first token query, because we said there are three. For each token, you have three: query, key, value. So the query is what am I looking for? The key is what information do I contain, and the value is if selected, what do I contribute? Now, the attention score between two tokens is the dot product of the first token query, what am I looking for, and the second token's key, which is what information do I contain. So a measure of semantic relevance here. So these scores are normalized, so they sum up to 1, which is softmax. Then they used to take a weighted sum of all values vector. The result is a contextualized representation enriched by everything the token has token attend to. So multiple simultaneous perspective. Now transformers run many attention mechanisms in parallel, typically 8 to 96 heads. Yeah. So each potentially specializing in different relationship types. So head one might focus on grammatical subject object structure. Head two might focus on conference tracking, which pronoun refer to which entities, and head three might focus on semantic predicates, which verbs apply to which argument. Head four might focus on positional proximity, near words versus distant words. Yeah. So these specialization are learned, not programmed. So researchers have studied attention heads in trained models and found a real functional specialization. One famous 2019 paper found a head in BERT that almost perfectly implements a dependency parser. It learns syntactic structure from language modeling alone. Now, the layered approach, yeah, side here, why depth matters, yeah. So a transformer has not one attention layer, but many, 12 to 96 layers. So each layer takes the previous layer's output as input. So early layer learns surface feature, punctuation, word categories, local phrases, structure. Middle layer learns semantic relations like conferences, named entities, factual association. Later layers learn task level abstraction. So by the end of the final layer, each token's representation has been enriched by the full context of the sequence. So processed through multiple levels of abstraction. So the model's understanding of a word is not static. It depends entirely on what's surrounding it. Now, we keep using the word token. Let us examine it precisely because tokens are the units of pricing, the units of context limits, and the unit of model capability. Now, we are going to talk about tokens, which is tokens are like the unit of everything. Yeah. Tokens, as we saw before, are not words. They are subword units, fragments determined by a statistical compression algorithm applied to the training corpus. This distinction matters practically and financially. Now, tokenization in practice is let us look at real example. So common English words, hello, there, is, and each typically is one token. So frequent that the compression algorithm keeps them whole. Now, the compound or rare words is, for example, unbelievable. It has three tokens, unbelieve, which is a root word, for example, and able. So now the proper nouns, for example, if there is new proper noun like ChatGPT, for example, has three tokens. It has a chat, the G, and the PT. Anthropic has two tokens, the ant and the horopic, yeah, assembled from recognizable fragments. Yeah. So, for example, for the code Python, if you have def calculate mean open bracket in Python, for example, has 4 tokens. The def is one, the calculate is another one, and the underscore mean is another one, and then you have the open bracket. Yeah. So the function signature is for processable unit. That's again for the code. Yeah. So numbers like 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 have 4 tokens. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0 split at arbitrary boundaries. The fragmentation is why arithmetic with large numbers is genuinely difficult for LLMs. Yeah. So the model does not process numbers as numbers, but as arbitrary token sequence. So it's very important to know that. So uh, don't forget, like LLM are like for text and not numbers. Yeah. So that is why they use tokens, and tokens are not they are not aware of numbers. They just as we are looking here, they just arbitrarily chunk or cut the sequence of numbers. So you have also for non-English, a single Chinese character is typically 1 to 2 token. This is actually more efficient than English. Chinese characters carry more meaning per token, which is why models are relatively good at Chinese despite it being a minority of training data. Yeah, so the 3 practical implications are billing. For example, every major LLM API like Claudia, GPT-4, Gemini charges you per token. So English averages 1.3 tokens per word. Say, for example, if you have a 10,000 word document is roughly 13,000 input token. Yeah. So at GPT-4 Turbos, which is they charge you like £10, $10 per million input token. That is, this one comes, this 10,000 document comes to 13p per document. So if you process, for example, 100,000 documents per day, and you are spending 13,000 per day on input token alone. So token awareness is financial awareness. Yeah. So if you're very big data, like say this is again, let me repeat here. The numbering is critical here. Yeah. So what we say is like English average is 1.3 token. Yeah. So if you have a document, which is normal 10,000 word document, yeah, is in terms of token is 13,000. So if they charge you tens, for example, dollars per million input token, so the 13,000 is going to be 13 cent per document. Yeah. So if you're going to process 100,000 document, yeah, of that nature, which is each one is 13p, yeah, per day, and you are spending, for example, 13,000 per day on an input token alone. So you need to be aware of this financial side of the token. Yeah. So the second one is like the context limit. Yeah, the context window. So the amount of text a model can see in one inference call is measured in tokens. So how much data can LLM see? Yeah, in one inference call. So, for example, a 128 tokens, 128,000 tokens is roughly 96 words. Yeah. So 96,000 words is like a book. Yeah. So a million token, which is the entire Harry Potter series, Yeah, because what you are saying is 128,000 token is like 96,000 words. So if you have like 1 million token, which is the entire Harry Potter series, the limit constraint, which is the limit constraint. So what you can include in a single code. So if they say, for example, the window, the context window is 1 million token, what they mean is like he can put into that window like Harry Potter series, all of it in one place. Yeah. So that is like the 1 million, the context limit, which is how LLM operates. Yeah. So that's again, it is very important to consider this one because some windows you might see like it is 128,000 tokens. It is like as I said before, 96,000 words, which is a book, novel book. Yeah. So you can put, if it is 1 million though, which is like Harry Potter series. So it will help you understand the limit, the context limit here. Yeah. Now the third one is prompt engineering. Yeah. Again, the concise prompts use the one you put. Yeah, the question you ask. So the concise prompt use fewer tokens. So this is the concise prompts. Yeah. So at scale, token efficiency and cost efficiency are the same thing. Yeah. So for high volume production system, every token you remove from a prompt multiplied by the millions of daily calls represent a meaningful cost savings. So if you, again, I'm going to repeat this one. So for high volume production system, for example, every token you remove from a prompt, yeah, multiplied by the millions of daily calls, yeah, because you are going to do represent a meaningful cost savings. Now, the context window defines the boundary of what the model can see at once. So this brings us to one of the most important and most misunderstood properties of LLM, their relationship to memory. We are going to focus now on the context window. So every LLM has a hard limit on how many tokens it can process in a single inference call. So this limit, the context window, applies to the combined length of your input. This is like your prompt, documents, conversation history as well. So all of them, they are like the context window. So, and the output, the response being generated as well. So everything together are the context window. So everything inside this window is visible to the model. So everything outside is invisible and as if it does not exist. So the memory illusion is the most important misconception. This is the single most important thing to understand about LLM that is most commonly misunderstood, even by experienced developers. LLM have no persistent memory. Yeah. So they don't have any persistent memory between conversations. Yeah. They do not remember you. They don't remember yesterday. They don't remember this morning. Each inference course is completely stateless. So the model started with zero knowledge of any previous interaction. What feels like memory is when Claudia or ChatGPT refers back to something you said 10 messages ago is an illusion created by the application layer. So the application resends the entire conversation history as part of every new request. So the model is not remembering anything. It is rereading the conversation from scratch with every message. Yeah. So the implication here is as a conversation grows longer, the history consumes more of the context window. So eventually the oldest messages are truncated or dropped to make room for more recent content. This is why very long ChatGPT conversations sometimes seem to forget things from early on. Those messages were cut. So what fits in context window, yeah, is like 2048 tokens was ChatGPT 3 2020, a single magazine article plus a response, which is 4096 tokens. It was like GPT 3.5 2021. A short story or a few documents, for example, 32,768 tokens GPT 3.5 Turbo, and a decent length report like 128,000 tokens GPT-4 Turbo, an entire novel around 96,000 words, like 200,000 tokens versus GPT-4 Turbo, an entire novel. So the Claudia 3 Opus, which is 200,000 tokens, a full academic textbook, so 1 million tokens, which is Gemini Ultra, the complete Harry Potter series. So a million token context window changes what is architecture possible. You can pass an organizational entire policy library, yeah, into a single call. You can include a full year of meeting transaction for the strategy analysis. You can analyze a complete software code base for security review. So the quadratic challenge, why large context costs more, is self-attention is computationally quadratic in sequence length. So double the context window and attention computation quadruples. Yeah. This is why large context windows are expensive to use and why providers charge more for long context requests. So the engineering innovation that enables millions tokens window, sparse attention, sliding window attention, linear attention approximation are among the most active research areas in the field today. Now, so this is again an important part to remember, yeah, with large language model and costing. So if you double the context window, yeah, from if you double it, then what happens is the attention competition quadruples. We shouldn't forget that one. That's why the money will be more in this size. Yeah. So now we have now covered what LLMs are, how they work, and what makes them large. How the transformer attention mechanism function, what tokens are, and the context window constraint. Let us close by surveying what these models can actually do with a specific prompt you can try. So what LLM can do, the capability side. So each capability I'm about to describe is accessible right now. So the example prompt in each card is a literal prompt you can paste in Claudia, ChatGPT, or Gemini today and receive high quality response in seconds. Let me walk you through all 8. So text generation. So write a cover letter for a software engineer with 5 years of Python experience applying to a senior role at fintech company. So emphasize risk management system and regulatory compliance familiarity. Now, without LLM, 30 to 60 minutes per letter, with LLM under 10 seconds. So the quality is sufficient for a strong first draft that a human then refines. So if you try this one, so a cover letter for a software engineer, look here. So we're very, if you need to give the LM very specific information, you need to have like 5 years of Python experience applying to a senior role, and the company is fintech. Yeah, so all this one makes a lot of difference. So also emphasize risk management system and regulatory compliance. So this one, if you were to do this one by yourself, I mean, you would know it will take a couple of hours, yeah. But for LLM, is just a matter of seconds, yeah. Number two is summarization. So you can summarize, for example, you can say summarize this 50-page regulatory reports into 5 bullet points. So look here now, this is the precision you need to give. So you are given this, it is 50-page regulatory report, and then you want like 5 bullet points, yeah? So each under 25 words. You can try, for example, remove this regulatory report, generic report, and see what will happen. But and then you can change the number 50-page to 2-page or 100-page, and each of the 5 bullets, yeah, it will be under 25 words, focusing. Now, this is the key part on compliance implications for a UK bank. Yeah. Now, the model reads a document it has never seen before and produces a competent summary for initial triage of large document volume. This is transformative. Hours of reading compressed to seconds. Yeah. So this is another use capabilities of LLM. Now translations. Unlike word-for-word machine translation, LLM can be instructed to preserve legal formality, much industry specific terminology, and adapt cultural register. So, for example, you can say translate this medical consent form from English to Arabic, preserving formal clinical register and using WHO standard terminology. Now, machines, they are not good at translating this specific one, but LLM, they are. So older translation tools cannot handle domain-specific register preservation at this level. So this is question answers from context as well. So the foundation of most enterprise LLM application, yeah, it is you can paste any document into the context and ask specific questions based on this product manual. What is the maximum operating temperature and what actions void the warranty? So the model reads and extracts, no indexing required. So no training on your document, just contextual reading. So you can give the document and ask questions based on that document, and it will give you a precise answer based on your document as well. So without creating any indexing or the RAG side to it. So now classification at a scale. This is also another one which is very useful. So classify this customer support ticket as billing, technical, account access, or general inquiry. Now, and then you can say assign priority, urgent, normal, or low based on the language used. Run this over 10,000 tickets per day, and you have an automated try system that previously requires a human team. So consistency and speed at a fraction of the cost. Yeah. So this is very interesting bit, and it's very important one as well, especially if you are working in support team. So it can classify the support ticket as billing, technical, account access, or general inquiry, and then give the priority like urgent is normal or low based on the language used. Yeah. So run this over 10,000 tickets per day. So this is again a very interesting one. So if you run this language used, run this. So if you give like the context, classify this customer support ticket as billing, technical, account access or general inquiry, assign priority, urgent, normal, or low, based on the language used. You give that inquiry to a language model, and then you can keep running these tickets, even 10,000, 50,000, 5,000 tickets per day. And you get those classification with their priority assigned. So the other one is step-by-step reasoning. A train leaves Manchester at 9:15 at 160 kilometers per hour. Second train leaves Birmingham at 9:45 at 2,000 kilometers per hour. They are 280 kilometers apart. So when and where do they meet? This is a classical question. So when you were like primary school children, we used to ask questions like that, and we used to compete against our friends and that, or our brothers and sisters. So now you can ask the same question in it's not, of course, it's not like this kind of very sophisticated kind of question, which requires a statistical or mathematical understanding. But which requires like a couple of days, sometimes hours, unless you're exposed to it beforehand. So in order to solve it yourself, it requires a very long time. But because you do it again and again, you learn how to do them, and then you become very expert on them. When you are a child, that is. So if you ask that question, this model works through this algebraically, showing all steps, yeah, chain of thought reasoning. So now the ability to solve multi-step problems by generating intermediate reasoning was one of the most surprising emergent capabilities discovered in large models. Yeah. So this is if you work these days, or if you use ChatGPT or Claudia or Gemini these days, what you see is like the reasoning behind the LLM. They give you what they're doing. Yeah. So this was like again those one of those surprising emergent capabilities which were discovered in large models. Yeah. So now the code generation is another one, right? A Python function that reads a CSV file with columns, date, amount, and category, filters rows where amount exceeds 500, groups by category, computes sum and mean per category, and returns a sorted dictionary. Now, working syntactically, correct code in 3 seconds with tests the docstrings and error handling if you ask for them explicitly. So they give you like in a very short period the code you want. Yeah. So creative ideas. Give me 10 product name ideas for a sustainable water bottle brand targeting urban professionals aged 25 to 40. Each name should be one or two words. Avoid dictionary words for trademark purposes, and evoke themes of clarity, movement, or mature. Unconstrained brainstorming and clutched by anchoring biases that make human ideations repetitive. Now, the key insight is none of this was programmed. None of these 8 capabilities were in the training objective. The model was trained to predict the next word. Translation, reasoning, classification, code generation, all merged from the single task at sufficient scale. These are almost certainly additional capabilities in models being trained right now that we have not yet discovered. So that uncertainty is what makes this field so conceptual to understand. So that is, I think, the end of our session today. I hope you have enjoyed it or gained something out of it. And see you next when we try to compare the different models in the market.